All right, so let's go ahead and get started for a second. So today, there's not a quiz today, but you'll probably have a short quiz in the actual lab section itself. So that's fine. It will be going over the content from the first couple of videos, right, on inheritance and polymorphism. But I figured I'd start off the lecture just by going over a couple of things that, I'm going to go over the foxes, the way the fox operates, right? The way I'm going to go over the decisions the fox makes in order to find your rabbit, okay? In a bit more detail. Now, a lot of students, I saw this last night as well. They tried what they tried to do is that a lot of them just copy pasted this and tried to reverse like what this was going on, and that's good for getting started, but it's not going to lead you to a sustainable option for victory because this algorithm is completely predicated on basically catching stuff as opposed to running away. So let's go ahead and look at how the fox catches your rabbit. So we've got a have seen rabbit variable and can see rabbit now, right? Have I seen the rabbit and can I see it now? Then the fox also keeps track of how far it is from the rabbit, what direction the rabbit is in, and the current direction the fox is going. And the constructor, all they've done is modify it so that it's currently going in a random direction. So it starts by heading in a random direction. All right. The first thing that it does is that it looks all around for the rabbit. Okay. So it sets can see rabbit now to false, and then it uses a for loop. Int I is equal to 0, and then it starts at the model.min direction. So it starts by looking north, and then it goes up to and includes the maximum direction, which is northwest. So it looks counterclockwise in all directions, and if the look function returns the rabbit, it sets I have seen the rabbit to true, and it sets the can see the rabbit now to true. This is a perfectly legal statement, although it's much more, I feel, better readable if you break it down into two statements rather than one big statement like that. It sets the direction to the rabbit to that direction, and it sets its distance to the rabbit to what gets returned by the distance call. These are, so distance and look, you're like, where are they? Well, they're an animal, and it accesses them, and the fox is able to access them by going essentially this dot look and this dot distance. Okay? So I'm going to skip over what it does if it has seen the rabbit, right? And if it hasn't seen the rabbit, or maybe it lost track of the rabbit at some point, its algorithm. So if it hasn't seen the rabbit, it just continues going in the direction it's set to be going, right? If I can't see the rabbit, I'm just going to keep going in the direction I was going. Okay. So if I can move in the current direction, I move in that direction. So that's another useful function. The can move, given a direction, can I move in that direction without, will that actually be a move I can make? Because if you say move in that direction and you can't move there, right? If you return a invalid direction for decide move, you're just not going to move. So if you can move in that direction, I go into that direction. Then notice what it does over here. Else, if I can't move in that direction, I ask can move on current direction 1. Okay? So current direction 1 is hi there. So I'll use that. I'll try that out after this.
Okay.
Okay. So if I can move in this direction, so if I can't go in this direction, I look 45 degrees clockwise and ask, can I move that direction? So if I can't move this way from my perspective, then I'm going to try going this way from my perspective. All right? And if I can go that way, I go that way. And that way I can get around basically an obstacle. I can go around an obstacle. Now if I can't go that way, then I go -1. I turn -1 degrees. Sorry, -1 for my turn as my argument for turn, which means I'm going 45 degrees counterclockwise. So I ask myself. So I try moving 45. So I try going diagonally this way instead. If I can't go this way or this way, I try going this way, which is actually a good strategy for you if you're trying to go in a specific direction. Otherwise, if it can't go in that direction, then it assumes it's basically hit a wall or something, and then it chooses a new direction at random, and then it asks, can I move? I'm going to start at that direction. If I can move in that direction, I'm going to go in that direction. Now this whole thing, instead of just like doing a loop over one direction and like just choose, the reason it does this as opposed to just like doing a loop and iterating through all the directions starting with north is that that would give it a bias, essentially. If we had something like this, else if else for int I is equal to model dot min direction, just like we had up there, right, up to the maximum direction, and then the algorithm is if can move in I, return I. Right? If that was its algorithm, then that would bias it towards moving north or northeast almost all the time. What it has here is that it chooses a direction pretty much at random, and then says, I'm going to use that as the starting point to check if I can turn in any direction. So it will try moving. And if that's not going to work, then somehow it got stuck, and it's just going to stay put. Okay. Now, if it does see your rabbit on the other, so that's if it can't see your rabbit or it lost the rabbit, right? If it lost your rabbit, it can't see your rabbit anymore. It's just going to keep going. It's going to try something else, right? So if it has seen your rabbit, if I have seen the rabbit at some point, I'm going to move towards its last known location, right? If the distance to the rabbit is greater than 0, I'm going to say distance minus minus and return going to that direction. Otherwise, I've gotten to the point, if I have seen the rabbit and I've gotten to the point where the rabbit where the rabbit was, if I've gotten to the point where the rabbit was and I, can't see him anymore, then I set that to false. I have seen rabbit to false, and I set the current direction to being a random direction. So if I completely lose track of your rabbit, I'm going to just choose a random direction and start going that way. Okay? So this means that basically if you can shake the fox, it's going to stop chasing you. Basically, if the fox sees you and then it stops seeing you, it's going to start just looking around at random again. So that's the way the fox works. Okay? So that's its strategy. So a couple of good strategies that I've seen use a couple of different aspects. The first is relying off the fact that basically that the look function means that the whole way the board works and the look function means that visibility isn't what you think it is. Okay? You've got something along the lines of, let's go ahead and see there. See if we've got the fox here, right? And I'm going to go ahead and I'm just going to double check my recording. Yep, that should work for that. Okay. So if we've got the fox here, right, its line of sight is essentially this, right? These dotted squares. And so on and so forth, stretching off until it hits something. That means actually if your rabbit's right here, the fox can't see you, right? In fact, this cone, notice that this is kind of like a growing cone and it gets bigger and bigger. There's this giant cone diagonal on each of the diagonals of the fox where the fox just can't see you. And that's before we take into account all of the, bushes that are blocking, line of sight. So, for instance, if I'm here, right, if the rabbit's here, he could move here, here, or here, or here, or here, or here, and now I'm out of line of sight. That means that I do know that what are the next 4 turns are going to be too, right? The next 4 turns for the fox are going to be here, 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 and then here, unless it sees me again. So if I can stay out of the line of sight of the fox, I basically get the next 4 turns to hide until it sees me again. That's not necessarily the distance that you might want to check for, but the shorter the distance is, the more power you have, the more accurately you can predict what it's going to be, what his next moves are going to be. So that means that basically a really good strategy, like something in the 90th percentile, will have will take into account the distance between the fox and you, and use that as a guide. Another big strategy will use basically you take advantage of the fact that you can dodge out of his line of sight. and may be able to break that off. And I guess the third strategy is also note that there are patterns. Is that basically if you can get the fox to just chase you, right, and you've got basically no obstacles in your way, or obstacles you can easily get around, then you basically will win, right? If to use MMO terms, if you can kite this thing, you will win, okay? Because this guy isn't going to do anything unpredictable. He's not going to set up a trap for you. You'll lose sometimes because sometimes he just spawns right next to you and you can't see him until he's on top of you. Okay, so that's my suggestions. Go ahead and get started. If you have trouble getting started, then here's what I suggest doing. Write a for loop. Look in every direction. If you see the fox in that direction, move away. This will at least confirm that you can get you can move away from the fox. It won't let you win because you're only moving now because you're running away from the fox. Then add on to that algorithm. If I can't move directly away, maybe try moving directly to the diagonals. Then add on to that. If I can't move to the diagonals, try moving perpendicular. And that will start getting you in the 10% range for survivability. Because you're only moving now when you can see the fox and the fox can see you. So you need to be moving, and then you need to realize you need to be moving all the time. So now, or at least all the time if the fox sees you. So, or at least if the fox sees you, you need to run until you're sure you're safe. So and that's something you can do. All right, and you will be working on this in the lab in your lab sections as well. So.